Broken conductors and three-phase loads. In this presentation, we're going to be looking at what happens to a balanced load when one of the conductors that connects to it is broken in either a Y or a delta formation. So let's start with the Y system, and we're going to start with a normal situation with the Y system, and that is a balanced 10 ohm load which has all the conductors still connected and operating normally. We have A, B, and C connected here, 208 volt line, which means we have 120 volt phase across each one of the individual resistors. Now, remember, since each one of these is 10 ohms, and because we have a full 208 volt line, all three of these loads will have 120 volts across them, and all three should have exactly the same current. Now, when we apply 120 volts to 10 ohms with Ohm's law, we get a total phase and line current of 12 amps. And this would be true for A, B, and C. Now, if we were to break one of the conductors that's supplying these loads, we would find that the current through the broken wire for that particular load would drop to zero. So there's now 0 amps that are being drawn by load A, which means phase current for A is 0, as well as the line current for line A would be 0 amps. Something interesting happens on the remaining two loads, and that's because we now have a series circuit. A series circuit is one where there's only one path for current to flow, and what we end up with is a basic question from level 1. 208 volts is divided equally across the two loads because the two loads are equivalent in ohmic value. They're each 10 ohms apiece. And when we apply a single voltage across the series circuit, the voltage will then split equally, rendering 104 volts. Now, if we wanted to work out the current for the line B and C conductors, that current would be the same in each conductor because it is in series. And if we wanted to calculate this value, we would need the total resistance. In a series circuit, the two resistances or impedance values add together, and since these are resistors, the sum is 20 ohms, giving me a current value of 10.4. If we were then to break a different conductor, and we call this an open line condition because we're actually breaking the line conductor as opposed to the phase. A bit of a trivial item to pinpoint here, but the reason we're going through all three diagrams is because in delta, the differences between all three are much more apparent. So in this series circuit, again, we have a series connection between A and C this time, 104 volts across each of those two resistors. And again, the same math renders 10.4 amp line current on line conductors A and C. Well, let's then take a look at what happens in a delta system when we do the same type of breaking. So in a normal situation with a delta arranged series of balanced loads, 10 ohms apiece, 208 volts would then mean phase voltage of 208. And when we apply Ohm's law with 208 and 10 ohms, we would get 20.8 amps. That would be the phase current. The line current would be calculated by applying root 3 to our 20.8 amps, and that current would be flowing on the brown conductors we see here, A, B, and C. Since it's a balanced load and everything's connected, the value of current should be exactly the same in each of the line conductors. Now, when we have an open phase condition in a delta balanced load, the individual phase where we have broken has 0 volts across it, so load 2, 0 volts, but in addition to that, it has 0 amps. And we get a weird situation where all three conductors are still going to continue to carry current. However, they're not all going to be equal. So let's look at the voltage across load 1. It hasn't changed at all from a normal condition. It is still 208 volts, which means the current that's flowing through the first resistor would also remain unchanged, and we can see that. Resistor 3, the voltage has not changed across that resistor either because line A is still solidly connected. That means that 20.8 would be the expected phase current. At this point, we now have to look at what does the circuit look like? Well, the only thing that line A is now supplying is the phase current for resistor 3. And so that would then mean that IA 20.8. The exact same conclusion we can come to for line conductor B, and that's because the phase current of resistor 1 is the only thing the line conductor B is now supplying. And so 20.8 is the answer for this as well. The one that bucks the trend and is kind of odd to wrap our minds around is that line conductor C is now supplying both load 1 and load 3. And in the typical fashion of delta connections, that means that the current value is combining at this point, and we have a root 3 value larger. So the remaining line conductor that supplies two loads has the original line current from the unchanged or normal system. So 36.02 amps would be traveling on line conductor C. Now, what happens if instead of breaking the phase conductor, we break the line conductor? When we break the line conductor, yet another rather odd situation occurs. In this situation, we still have connections through all of our individual loads, which are 10 ohms apiece. What this means is that as soon as we remove this third line, we now have a series parallel circuit or combination circuit that would be more akin to a question in level 1. What we have to do is resketch the diagram to show the individual resistance values and then break the total value of resistance down to a single equivalent value. We combine 1 and 3 in series, giving me 20 ohms, and then 20 and 10 in parallel gives me 6.66 ohms. This then means that I have 31.23 amps because the voltage across this combination circuit from here to here is 208 volts. I then have to apply my individual voltage values to each of these resistors. And if it's 208 volts here, it's 208 volts here. So my 10 ohm resistor, my number 2, has 208 volts. And the same logic that we applied in the original situation of voltage splitting, if I have 208 volts across these two resistors and their equivalent in resistance, they must have 104 volts across them also. This then means that resistor 1 has 100 volts, resistor 2 has 208 volts, and resistor 3 has 104 volts. The amount of current that we would expect to flow in this system would then be equivalent for both A and B. Since it's a combination circuit and there's only one entrance and one exit to the circuit, we have exactly the same value of current on both of the remaining line conductors. Open conductors are helpful to know at least the premise for what to expect in case we come into a situation where we're attempting to troubleshoot something like a heating system, a three-phase heater, or a three-phase motor, and we are getting odd, unbalanced current values, even though we know the load is actually balanced.